Long before skyscrapers pierced the clouds and highways carved through continents, humanity stood at the edge of extinction. Picture this: glaciers grinding southward like planetary jaws, temperatures plummeting so fast that entire forests froze mid-growth, and a sun dimmed by volcanic ash that refused to fade. This wasn't some prehistoric fantasy or distant alien world. This was Earth roughly 12,800 years ago, when the planet decided to hit the reset button on climate. The world was warming, ice sheets were retreating, and early humans were finally catching their breath after surviving the last ice age. Then, without warning, everything reversed. Temperatures nosedived, ice surged back across the Northern Hemisphere, and humanity, still fragile and scattered, faced a catastrophe that would reshape the course of civilization itself. Scientists call it the Younger Dryas, but the name doesn't capture the terror. A 10,000-year winter that almost erased us from existence. If you think you know the cold, think again, because what happened during this frozen nightmare makes modern winters look like mild inconveniences, when the world froze overnight. The Younger Dryas didn't announce themselves with warning signs or gradual transitions. It struck like a geological ambush, flipping the climate from warming to freezing in what scientists estimate was less than a decade, possibly as quickly as 3 years in some regions. Imagine experiencing autumn one season, then suddenly finding yourself trapped in an Arctic wasteland the next, with no understanding of why or when it might end. This wasn't the slow creep of seasonal change. This was climate whiplash on a planetary scale. Ice cores drilled from Greenland reveal the violence of this transition through oxygen isotope ratios, which serve as ancient thermometers locked in frozen time. These cores show temperature drops of up to 15 degrees Celsius in certain areas, a shift so abrupt that entire ecosystems had no time to adapt. The transition hit the Northern Hemisphere hardest, particularly around the North Atlantic. Europe, which had been experiencing relatively mild conditions as the last ice age loosened its grip, suddenly found itself buried under renewed glaciation. The Scandinavian ice sheet, which had been steadily retreating northward, reversed course and began advancing again. In North America, the Laurentide ice sheet, a continent-spanning monster of ice that had covered Canada and much of the northern United States, stabilized and even expanded in certain regions. Evidence from sediment cores taken from lakes across North America shows layers of glacial debris that correspond precisely to this period, indicating that ice not only stopped melting, but actively ground forward once more. The speed of this change is what makes it scientifically fascinating and historically terrifying. Modern climate models struggle to fully replicate the mechanisms that could cause such a rapid flip. The leading theory involves the catastrophic disruption of ocean circulation, specifically the Atlantic meridional overturning circulation, which includes the Gulf Stream. This massive current system acts like a conveyor belt, moving warm water from the tropics northward and cold water southward. When the system functions normally, it keeps northern Europe and the North Atlantic region relatively temperate. But something caused this conveyor belt to shut down almost completely, and when it did, the entire Northern Hemisphere paid the price. The trigger likely came from the melting Laurentide ice sheet itself. As temperatures warmed during the transition out of the Ice Age, this massive ice sheet began releasing colossal volumes of fresh water. This wasn't a gentle trickle. Geological evidence points to catastrophic outburst floods that dump millions of cubic kilometers of fresh water into the North Atlantic. One theory suggests that a massive proglacial lake, known as Lake Agassiz, which had formed along the southern margin of the retreating ice sheet, suddenly breached its ice dam. The resulting flood would have been biblical in scale, routing through the Great Lakes region and into the North Atlantic via the St. Lawrence River Valley. Sediment analysis from the ocean floor shows thick layers of ice-rafted debris and freshwater indicators that match this timeline perfectly. This influx of cold fresh water had a devastating effect on ocean circulation. The Atlantic meridional overturning circulation depends on differences in water density to function. Warm, salty water from the tropics flows north, cools down, becomes denser, and sinks to the ocean depths before flowing back south. But when massive amounts of fresh water, which is less dense than salt water, suddenly flooded the North Atlantic, the water at the surface became too light to sink. The conveyor belt stalled. Without warm water flowing northward, the climate around the North Atlantic basin plunged into deep freeze. Europe, which should have been warming, instead experienced conditions similar to Siberia. Britain, which had been seeing the return of forests and wildlife, was suddenly locked in permafrost. The atmospheric effects compounded the disaster. As temperatures dropped, snow accumulated faster than it could melt, increasing the planet's albedo, the amount of sunlight reflected back into space. White snow and ice reflect far more solar radiation than dark soil or ocean water, creating a feedback loop that drives temperatures even lower. The polar jet stream, which normally flows in relatively stable patterns, became wildly unstable and shifted southward. This brought Arctic air masses deep into regions that had never experienced such cold. Pollen records from bogs and lakes across Europe show the sudden disappearance of tree species and their replacement with tundra vegetation almost overnight in geological terms. For the human population scattered across these landscapes, the Younger Dryas represented an existential crisis. These were Paleolithic peoples, still living as hunter-gatherers, still dependent on the seasonal movements of game and the availability of wild plants. They had survived the worst of the Ice Age, developed sophisticated tools, and were beginning to establish more permanent settlements in favourable locations. Then the world turned against them again. Game animals disappeared or migrated to regions beyond reach. Plant foods became scarce as forests died back and were replaced by barren tundra. Water sources froze solid for longer periods. Even fire became harder to maintain as wood became scarce and conditions grew harsher. The archaeological record from this period shows clear signs of population stress. Settlement sites that had been continuously occupied for generations were suddenly abandoned. Tool assemblages show increased use of lower quality materials, suggesting that preferred stone sources were no longer accessible. There's evidence of increased violence at some sites. Human remains showing trauma consistent with interpersonal conflict, likely as groups competed over dwindling resources. Some researchers point to this period as a potential explanation for the extinction of several human cultures and the emergence of new ones, as populations were forced to adapt, migrate, or perish. The Younger Dryas wasn't just cold, it was a civilizational bottleneck that tested whether humanity had what it took to survive. The science of sudden climate collapse. Understanding how the Younger Dryas happened requires piecing together evidence from dozens of scientific disciplines, each contributing fragments to a puzzle that spans continents and thousands of years. The picture that emerges is one of Earth's climate systems behaving like a light switch, capable of flipping between states with shocking rapidity. This challenges the older view of climate as something that changes gradually, almost imperceptibly. Instead, the Younger Dryas demonstrates that Earth's climate can exhibit what scientists call threshold behaviour, stable for long periods, then suddenly shifting to an entirely different state when certain conditions are met. The evidence comes first from ice cores, which serve as the gold standard for understanding ancient climate. When scientists drill deep into the Greenland and Antarctic ice sheets, they're essentially time travelling through layers of compacted snow that fell year after year, century after century. Each layer traps tiny air bubbles, preserving samples of the ancient atmosphere. By analysing the ratio of different oxygen isotopes in the ice, researchers can determine past temperatures with remarkable precision. The Greenland ice cores show the Younger Dryas boundary as a dramatic shift in these isotope ratios, happening over a span measured in years rather than centuries. Some researchers argue the transition took less than a single decade. Complementing the ice core data are sediment cores pulled from lake beds and ocean floors across the Northern Hemisphere. These cores contain layers of material that settle year after year, creating annual bands similar to tree rings. By examining the types of pollen, the species of microscopic organisms, and the chemical composition of each layer, scientists can reconstruct what the environment was like when that sediment was deposited. During the Younger Dryas, lake sediments across Europe show a sudden transition from warm weather species to cold-adapted ones. Oak and elm pollen vanishes, replaced by grasses and shrubs typical of tundra environments. In the ocean, warm water plankton species disappear from the fossil record, replaced by cold water varieties. The physical evidence of glacial re-advance is carved directly into the landscape. Geologists have identified moraines, ridges of rock and debris pushed forward by advancing glaciers, that date precisely to the Younger Dryas period. These moraines exist in locations where glaciers had previously retreated, proving that ice sheets stopped melting and began growing again. In Scotland, moraines show that glaciers that had disappeared returned and carved fresh valleys before retreating again when the Younger Dryas ended. In Scandinavia, the ice sheet margin advanced southward by hundreds of kilometres, obliterating forests that had begun to re-establish themselves. The ice didn't just persist, it actively expanded. Ocean sediment cores provide smoking gun evidence for the freshwater pulse theory. Cores taken from the North Atlantic show layers rich in ice-rafted debris, rocks and sediment carried out to sea by icebergs and dropped to the ocean floor as the ice melted. These layers correspond exactly to the onset of the Younger Dryas, supporting the idea that massive amounts of ice and meltwater suddenly entered the Atlantic. Chemical analysis of these sediments reveals anomalously low salinity markers, confirming that freshwater diluted the ocean surface. This freshwater cap would have prevented the normal sinking of dense, salty water, effectively shutting down the Atlantic meridional overturning circulation. Computer models have helped scientists understand the mechanics of this shutdown. When researchers input a massive freshwater pulse into climate simulations of the North Atlantic, the models replicate the sudden cooling observed in the geological record. The conveyor belt of ocean circulation stalls, warm water stops flowing northward, and surface temperatures around the North Atlantic basin plummet. The models also show that once this shutdown occurs, the system can remain in this altered state for thousands of years, held in place by feedback mechanisms. The cold conditions promote more ice formation, which increases albedo, which causes more cooling, which promotes more ice. Breaking out of this cycle requires the system to be pushed past another threshold in the opposite direction. Atmospheric circulation patterns during the Younger Dryas can be inferred from multiple lines of evidence. Wind patterns leave signatures in the orientation of sand dunes, which can be dated using luminescence techniques. During the Younger Dryas, dune fields across North America and Europe show wind patterns consistent with a southward shifted jet stream, bringing Arctic air masses deep into mid-latitudes. Dust deposits in ice cores show increased atmospheric turbulence and aridity, suggesting that cold, dry conditions dominated large regions. The combination of cold temperatures and shifted wind patterns would have created a climate radically different from what preceded it. The rate of change is what makes the Younger Dryas so relevant to modern climate science. Today, we're witnessing rapid climate change driven by human activity, and the question of whether the climate system could flip to a new state is no longer theoretical. The Younger Dryas proves it has happened before. If the Greenland ice sheet were to melt rapidly due to modern warming, it could theoretically dump enough fresh water into the North Atlantic to disrupt ocean circulation again. While the specifics would differ, the starting conditions are not the same. The basic mechanism remains a concern. The Younger Dryas serves as a stark reminder that Earth's climate is not a stable, predictable system, but one capable of violent, rapid shifts that can reshape continents and destroy civilizations. The end of the Younger Dryas was as abrupt as its beginning. Ice cores showed that temperatures shot upward in roughly the same time frame it took for them to drop, possibly within a single decade. This suggests that whatever mechanism held the cold state in place suddenly released, allowing the climate system to snap back. The most likely explanation involves ocean circulation restarting. As the ice sheets continued their long-term retreat and the freshwater pulse dissipated, Salinity in the North Atlantic gradually increased. Eventually, conditions reached a point where dense water could sink again, restarting the conveyor belt. Warm water began flowing northward once more, temperatures spiked upward, and the ice retreated rapidly. The Younger Dryas ended, but its impact on human development was only beginning to be felt. Collapse of the hunter-gatherer world. Before the Younger Dryas struck, late Paleolithic humans across the Northern Hemisphere had achieved a level of stability that their ancestors would have considered unimaginable. These weren't primitive cave dwellers barely scraping by. They were sophisticated hunter-gatherers with complex social structures, refined tool technologies, and intimate knowledge of their environments. In Europe, the Magdalenian culture had developed exquisite artistic traditions, creating cave paintings of such skill that modern artists still marvel at them. In the Near East, Natufian peoples were beginning to experiment with sedentary living, constructing permanent structures and developing early forms of food storage. North American Clovis people had mastered mammoth hunting with specialized spear points of remarkable craftsmanship. These cultures were thriving, expanding, and on the cusp of major cultural innovations. Then the cold returned and shattered everything. The immediate impact on food resources was catastrophic. Hunter-gatherer economies depend on biodiversity and abundance. Successful groups maintain detailed seasonal calendars tracking when specific plants fruit, when fish spawn, when game animals migrate, and where resources can be found throughout the year. The Younger Dryas obliterated these patterns. Plant communities that had taken thousands of years to establish died back within years. Animals that humans had hunted for generations either went extinct or fled to refugia beyond reach. Lakes and rivers that had provided reliable fish stocks froze for longer periods or changed their character entirely. The intricate knowledge systems that hunter-gatherers had developed, passed down through generations, suddenly became obsolete as the world transformed into something unrecognizable. Archaeological sites across Europe show the devastation in material culture. The rich assemblages of tools, ornaments, and art that characterized the late Paleolithic became impoverished during the Younger Dryas. Sites show fewer exotic materials, suggesting that trade networks collapsed as groups became isolated. The quality of stonework sometimes declines, indicating either loss of knowledge as populations crashed, or simply that people were too stressed and mobile to invest time in creating elaborate tools. Some regions show complete abandonment. Areas that had supported human populations for thousands of years suddenly have no archaeological evidence of occupation. The people either moved or died, and in many cases, they likely did both. The Magdalenian culture of Western Europe, which had flourished during the warm period before the Younger Dryas, effectively collapsed. Their sophisticated reindeer hunting economy had depended on the seasonal movements of vast herds across the landscape. When the cold returned, these herds dispersed or declined, and the carefully balanced system fell apart. Cave art production, which had reached extraordinary heights with masterpieces like those at Lascaux and Altamira, essentially ceased. The latest dates for most major cave painting sites fall just before or early in the Younger Dryas period. This wasn't coincidence, it reflects cultural collapse. The surplus time, resources, and social organization required to create such art vanished when survival became desperate and immediate. In the Near East, Natufian culture faced its own crisis. These people had been pioneers of sedentism, building permanent structures and developing intensive wild grain harvesting strategies. They had created villages, burial grounds, and storage systems. But the Younger Dryas transformed the Levantine landscape from Mediterranean woodland to cold, dry steppe. The stands of wild wheat and barley that Natufians had harvested so productively shrank and became unpredictable. Villages that had been occupied year-round were abandoned or reduced to seasonal camps. The population that had been growing and consolidating fractured and dispersed. Many researchers believe this crisis forced a critical adaptation, the beginning of agriculture. With wild foods no longer reliable, some Natufian groups may have begun deliberately planting and tending crops, initiating the Neolithic Revolution. The Younger Dryas didn't just collapse the hunter-gatherer world. It forced innovations that would eventually transform humanity. North American populations faced equally devastating challenges. The Clovis culture, known for its distinctive fluted projectile points and efficiency at hunting megafauna, appears to have fragmented during the Younger Dryas. Mammoth populations were already declining before the cold snap, but the climate crisis accelerated their demise. As megafauna populations crashed, Clovis peoples had to adapt their subsistence strategies rapidly. The archaeological record shows a transition from specialized big game hunting to more generalized foraging strategies. The elegant Clovis points are replaced by a variety of regional styles, suggesting that the cultural unity that had characterized Clovis peoples gave way to localized adaptations. Some researchers propose that the Younger Dryas was a factor in the extinction of North American megafauna, though the debate continues. What's clear is that human hunting pressure, combined with rapid climate deterioration, created a deadly combination for Ice Age giants. Migration became a survival strategy. As northern regions became uninhabitable, populations were forced southward into areas already occupied. This created cascading displacement effects as groups pushed into each other's territories. Genetic studies of modern populations show evidence of population bottlenecks and migrations that correspond to this period. In Europe, populations retreated to southern refugia in Iberia, Italy, and the Balkans, areas where warmer conditions persisted even during the worst of the cold snap. These refugium populations would later expand northward when conditions improved, but the genetic diversity lost during the contraction was never fully recovered. The Younger Dryas acted as a genetic filter, eliminating lineages and reducing human diversity in ways that still echo in modern populations. The psychological impact on these populations can only be imagined. For people whose oral traditions and collective memory span generations, the return of Ice Age conditions must have seemed like the world itself was dying. Their understanding of the world was built on cycles and patterns. Seasons returned, animals migrated, plants grew in their time. The Younger Dryas broke these patterns. Elders who had guided their people through hard times had no framework for understanding or predicting what was happening. Spiritual and shamanic traditions likely struggled to explain why the gods or spirits had turned against humanity. This cognitive and spiritual crisis may have been as devastating as the physical one, undermining the cultural foundations that held communities together. The very idea that the world was reliable, predictable, and survivable was shattered. Those who survived had to rebuild not just their material culture, but their entire understanding of reality. Ice sheets advance again. The Younger Dryas represented a stunning reversal of what had seemed like an inexorable trend toward warmth. For thousands of years before this event, the massive ice sheets that had dominated the Northern Hemisphere during the last glacial maximum had been steadily retreating. The Laurentide ice sheet, which had covered Canada and extended as far south as modern New York and Chicago, had been melting and fragmenting. The Scandinavian ice sheet had withdrawn from northern Europe. Mountain glaciers worldwide were shrinking. Then suddenly, this retreat halted and in many regions reversed. Ice that had been disappearing began growing again, grinding forward over landscapes that had just begun to recover from millennia of burial beneath frozen masses. The Laurentide ice sheet's behavior during this period is documented through multiple lines of evidence. Glacial geologists have mapped moraines, ridges of debris pushed forward by glacier margins across Canada and the northern United States. Dating these moraines using techniques like radiocarbon dating and cosmogenic nuclide exposure dating reveals that many formed during the Younger Dryas. This means glaciers that had been retreating suddenly stabilized and in some cases advanced. In the Hudson Bay region, the ice sheet actually thickened, increasing its weight on the underlying crust. This is known because crustal rebound measurements, tracking how the land surface has risen since the ice melted, show anomalies consistent with increased ice loading during this period. The Earth's crust had begun lifting as ice weight decreased, then was pushed back down as ice mass increased again, during the Younger Dryas. In Scandinavia, the evidence is even more dramatic. The Scandinavian ice sheet had retreated significantly during the warming phase, exposing much of Norway, Sweden, and Finland. When the Younger Dryas began, temperatures dropped so severely that the ice sheet reversed its retreat. Moraines in Norway show that glaciers advanced hundreds of kilometres, carving new valleys and scouring landscapes that had been ice-free for centuries. Norwegian fjords preserve sediment records that show layers of glacial flour, finely ground rock dust produced by active glaciation, dating precisely to the Younger Dryas period. These glaciers didn't just persist, they actively grew, flowing downhill and reclaiming territory. The ice margin in southern Sweden advanced southward, pushing into regions where vegetation had begun to establish. Forests that had started growing were bulldozed and buried beneath advancing ice. Mountain glaciers worldwide responded to the Younger Dryas cooling. In the Alps, glaciers that had been shrinking suddenly expanded, advancing down valleys and destroying vegetation. Evidence comes from preserved tree stumps found at glacier margins, killed by advancing ice and buried in moraine sediments. Radiocarbon dating of these stumps places their death at the onset of the Younger Dryas. In Scotland, glaciers that had completely disappeared reformed and carved fresh cirques and valleys before melting away again when warmth returned. The Scottish Highlands show clear geological evidence of this reglaciation. Polished bedrock, transported boulders called erratics, and moraines, all dating to this narrow time window. In the Andes of South America, mountain glaciers expanded dramatically, leaving moraines at lower elevations than the preceding or following warm periods. The mechanism driving this ice growth was primarily the collapse in temperature combined with increased precipitation in some regions. For a glacier to grow, snowfall must exceed melting. The Younger Dryas provided both colder temperatures that reduced summer melt and in some regions increased winter snowfall. The disrupted atmospheric circulation patterns brought moisture-laden storms to areas where snowfall accumulated year after year. Each winter's snow compressed into ice, adding to glacier thickness. Over decades and centuries, this accumulation transformed into rivers of ice, flowing downhill. Gravity pulled these ice masses forward, and their sheer weight caused the ice to deform and flow like extremely slow, viscous fluid. The rate of advance varied by region and by the individual characteristics of each glacier, but the overall pattern was consistent. Ice was winning again. The expansion of ice had profound effects on ocean circulation beyond the initial freshwater pulse that may have triggered the event. As glaciers grew, they carved icebergs into the ocean, particularly from the margins of the Laurentide ice sheet flowing into the North Atlantic. These icebergs carried debris, rocks and sediment frozen into the ice, which was deposited on the ocean floor as the ice melted. Oceanographers have identified layers of ice-rafted debris in North Atlantic sediment cores that correspond to the Younger Dryas period, showing that iceberg discharge continued throughout the cold event. This ongoing freshwater input would have helped maintain the disrupted ocean circulation, keeping the Atlantic meridional overturning circulation in its weakened state. The system was locked in a cold mode, with multiple feedback mechanisms keeping it there. The persistence of these ice masses for over 1,000 years demonstrates the stability of the cold state once established. This is what makes the Younger Dryas so concerning from a modern climate perspective. It shows that Earth's climate can get stuck in an altered configuration for long periods. The ice didn't just grow and then immediately melt when conditions changed slightly. It persisted, maintained by feedback loops, until conditions shifted enough to overwhelm those stabilizing mechanisms. When the end finally came, it was as abrupt as the beginning. Ice cores show the termination of the Younger Dryas happening over decades, with temperatures shooting back up rapidly. The ice sheets began their final retreat, this time not to return. But the 1,000+ years of cold had left permanent marks on the landscape and on the species, including humans, that survived. When Europe turned to tundra. The transformation of Europe during the Younger Dryas was so complete that the continent became virtually unrecognizable. Regions that today support dense forests, agricultural lands and cities became frozen wastelands more similar to modern Arctic tundra than to anything currently found in Europe. This wasn't a gradual transition allowing ecosystems to adapt. It was a climate catastrophe that killed forests where they stood and replaced diverse ecosystem with sparse, hardy vegetation capable of surviving months of frozen darkness and intense cold. The pollen record preserved in lake sediments tells this story with brutal clarity, showing the botanical equivalent of mass extinction, followed by the emergence of an entirely different plant community. Before the Younger Dryas, much of Europe had been experiencing relatively warm conditions. Tree pollen dominates sediment cores from this period, showing that oak, elm, birch, and pine forests had spread across the landscape as the ice sheets retreated. These weren't sparse woodlands, but dense forests supporting diverse animal communities. Deer, wild boar, and aurochs browsed in these forests. Birds nested in the canopy. The forest floor was rich with ferns, flowers, and fungi. Rivers flowing through these forests supported fish populations. This was a productive, thriving environment where human populations could find abundant resources. The late glacial interstadial, as this warm period is called, represented a preview of the warm Holocene climate that would eventually prevail. But that preview was cut brutally short. The pollen record shows what happened next with stark precision. Within layers representing just a few years of deposition, tree pollen vanishes and is replaced by pollen from grasses, sedges, and low shrubs typical of tundra environments. This isn't gradual replacement, it's a catastrophic die-off. The trees didn't slowly give way to cold-adapted species. They died, and a completely different plant community colonized the landscape. Birch, being relatively cold-tolerant, persisted longer than oaks and elms, but eventually even the birch forests collapsed. What emerged was a landscape of grasses, mosses, and dwarf shrubs, plants that could survive frozen soil, intense cold, and short growing seasons. Wildflowers that could complete their reproductive cycle in weeks appeared in the pollen record, plants that could take advantage of brief summer conditions before the cold returned. The physical landscape itself transformed as the climate shifted. Without tree roots to stabilize slopes, erosion increased dramatically. Sediment cores from lakes show thick layers of silt and clay deposited during the Younger Dryas, washed in from destabilized slopes. Rivers changed their character from meandering vegetated channels to braided, unstable streams choked with sediment. In some regions, massive solifluction lobes developed, features where the active layer of soil above permafrost slowly flows downhill during brief summer thaws, creating distinctive lobe-shaped deposits. These features are common in Arctic regions today, but their presence in Central and Western Europe during the Younger Dryas shows just how severe conditions became. The ground was frozen solid for most of the year, and even summer couldn't thaw it beyond a thin surface layer. Animal populations underwent massive reorganizations. Species that had adapted to forest environments disappeared from most of Europe, either going extinct or retreating to small refugia in southern regions where conditions remained marginally better. Reindeer and musk oxen, species adapted to tundra conditions, expanded their ranges southward into regions where they had been absent for thousands of years. Woolly mammoths, which had been declining throughout the warming period, found temporary respite as tundra conditions returned, though this wouldn't save them from eventual extinction. The bones of Arctic fox appear in cave deposits far south of their modern range. Lemmings, voles, and other small mammals adapted to cold grasslands became the dominant small herbivores. Predator populations crashed as prey became scarcer and more dispersed. The retreat to refugia is one of the most important biogeographic patterns from this period. As northern and central Europe became uninhabitable for many species, populations contracted into areas where warmer conditions persisted, primarily the Mediterranean peninsulas of Iberia, Italy, and the Balkans. These regions, protected by mountains and influenced by warmer Mediterranean waters, remained relatively mild even as Ice Age conditions returned farther north. Genetic studies of modern European plant and animal species show clear signatures of these refugia. Many species show reduced genetic diversity in northern populations compared to southern ones, consistent with northern populations being derived from small founder populations that recolonized from the south after the Younger Dryas ended. Some species show distinct genetic lineages corresponding to different refugia, reflecting the fact that populations were isolated in separate areas during the cold period. For human populations, the transformation meant catastrophic loss of resources. The forests that had provided nuts, fruits, game, and materials for tools and shelter disappeared. Rivers that had been productive fishing grounds became unstable, sediment-choked channels where fish populations crashed. The mosaic of different plant communities that hunter-gatherers depended on, providing different resources in different seasons, collapsed into monotonous tundra. Some human groups retreated southward along with other species, concentrating in the refuge areas. Others attempted to adapt to the new conditions, developing specialized tundra-adapted cultures focused on hunting reindeer and using every part of the animal for survival. But populations were dramatically reduced. Sites that had been occupied continuously for generations were abandoned. The archaeological record becomes sparse during the Younger Dryas, fewer sites, smaller sites, and less elaborate material culture. The duration of these tundra conditions, over 1,000 years, meant that multiple human generations lived and died without experiencing anything else. Young people would hear stories from elders about a time when forests existed, when summers were warm, when food was more abundant. But these would have seemed like myths or distant memories, increasingly detached from lived reality. The survival strategies and knowledge systems developed during the warm period became obsolete, replaced by new adaptations for surviving in harsh, unforgiving tundra environments. When conditions finally improved and forests began returning, the cultures that recolonized Northern Europe were different from those that had been forced out. The Younger Dryas didn't just pause European prehistory, it reset it, forcing cultural evolution in new directions, dictated by 1,000 years of survival in a frozen wasteland. The glacial lake that changed everything. The trigger for the Younger Dryas, the catastrophic event that transformed the climate so abruptly, likely came from a body of water that no longer exists. Lake Agassiz was a massive proglacial lake that formed along the southern margin of the retreating Laurentide ice sheet as it melted during the warming period before the Younger Dryas. At its maximum extent, this lake was larger than all the modern Great Lakes combined, containing more water than all current lakes on Earth. It stretched across parts of present-day Manitoba, Saskatchewan, Ontario, Minnesota, and North Dakota. The lake existed because meltwater from the ice sheet had nowhere to drain. The ice blocked northern outlets, forcing water to pool in the depression between the ice margin and the topography of the land. As the lake grew, it sought outlets to the south and east, draining at various times into the Gulf of Mexico via the Mississippi River system. But the lake's story was far from stable, and its catastrophic drainage may have reshaped the world climate. Evidence for Lake Agassiz comes from multiple sources that paint a picture of its immense scale. Ancient shorelines, wave-cut beaches that once formed at the lake's edge, are preserved across the landscape, marked by ridges of sand and gravel sorted by wave action. These shorelines occur at different elevations, showing that the lake level fluctuated dramatically over time. Some shorelines are hundreds of kilometers from others at different elevations, indicating that the lake expanded and contracted as outlets opened and closed. Dating these shorelines using radiocarbon methods on organic material trapped in the sediments provides a timeline of the lake's history. The highest shorelines predate the Younger Dryas, showing that the lake reached its maximum extent during the warm period when ice melting was most rapid. The mechanism for triggering the Younger Dryas involves a catastrophic drainage event from Lake Agassiz. The theory proposes that as the ice sheet continued to retreat, a new outlet opened to the northeast, allowing the lake to drain suddenly through the St. Lawrence River Valley into the North Atlantic. This wasn't a gradual flow, but a catastrophic flood that released thousands of cubic kilometres of fresh water in a geologically short period, possibly just months or years. The volume of water involved was staggering, estimated at enough to raise global sea levels by several metres if released all at once. Geological evidence supports this scenario. Thick layers of freshwater-derived sediment on the floor of the North Atlantic date to precisely the onset of the Younger Dryas, and sediment cores from the St. Lawrence Valley show massive flood deposits that match the timing. The impact of this freshwater pulse on North Atlantic circulation would have been immediate and devastating. The Atlantic meridional overturning circulation, which moves warm water northward as part of the Gulf Stream system, depends on density differences to function. Warm, salty water flows north, cools at high latitudes, becomes denser due to both the cold and the salinity, and sinks to the deep ocean before flowing southward. This sinking pulls more warm water northward, maintaining the circulation. But when Lake Agassiz dumped its freshwater load into the North Atlantic, it created a massive lens of low salinity water at the surface. Freshwater is less dense than salt water, so this layer refused to sink no matter how cold it got. The circulation system stalled. Without warm water being pulled northward, the North Atlantic region rapidly cooled. Europe and eastern North America, which benefit enormously from the heat transported by this circulation, plunged into Ice Age conditions. Computer simulations of this event consistently reproduce the observed climate changes. When researchers input a massive freshwater pulse into climate models representing conditions at the end of the last ice age, the models show rapid cooling around the North Atlantic and a weakening or shutdown of the overturning circulation. The magnitude and pattern of cooling match what the geological record shows, lending strong support to the Lake Agassiz drainage hypothesis. The models also show that once the circulation is disrupted, it doesn't immediately restart. Feedback mechanisms keep the system in the cold state until conditions change enough to overcome them. This explains why the Younger Dryas persisted for over 1,000 years, rather than being a brief cold snap. Alternative theories for the Younger Dryas trigger exist and remain subjects of active research. One hypothesis proposes an extraterrestrial impact, either a comet or asteroid, that occurred at the onset of the event. Proponents point to a layer of sediment enriched in materials like microspherules, nanodiamonds, and platinum group elements that they argue are impact markers. This Younger Dryas impact hypothesis has been controversial, with many researchers arguing that the proposed impact markers either aren't reliable indicators of impact or can be explained by other processes. The hypothesis has evolved over time, with recent versions suggesting an airburst event over the Laurentide ice sheet that could have triggered both wildfires and rapid ice melting. However, the Lake Agassiz drainage mechanism remains the leading explanation because it's directly supported by hydrological and oceanographic evidence. What's certain is that whatever triggered the Younger Dryas, the mechanism involved disrupting North Atlantic circulation through freshwater input. Whether that freshwater came from Lake Agassiz, from multiple smaller drainage events, or was accelerated by an impact event, the result was the same: a climate catastrophe that reshaped the Northern Hemisphere. The lake itself continued to exist in various forms throughout the Younger Dryas and beyond, draining catastrophically again at the end of the Younger Dryas, an event that may have contributed to the abrupt warming that finally ended the cold period. The final drainage of Lake Agassiz around 8,000 years ago involved releasing the remaining water into Hudson Bay, fundamentally altering North American hydrology and possibly influencing global sea level and climate once more. This ancient lake that no longer exists proved to be one of the most consequential bodies of water in human history. Megafauna in crisis. The Younger Dryas struck at a time when the great megafauna of the Pleistocene were already under pressure. Woolly mammoths, mastodons, giant ground sloths, saber-toothed cats, and dozens of other species had survived multiple glacial cycles over hundreds of thousands of years, adapting to advancing and retreating ice, changing vegetation patterns, and fluctuating resources. But the end of the Ice Age brought a new threat: increasingly sophisticated human hunters armed with refined weaponry and developing cooperative hunting strategies. The combination of climate change and human hunting pressure was already taking a toll on megafauna populations. Then the Younger Dryas added another layer of crisis, a sudden return to Ice Age conditions after these species had begun adapting to warming. For many, it was the final straw that pushed them toward extinction. But the relief was temporary and illusory. The Younger Dryas didn't simply restore Ice Age conditions. It created an unstable, unpredictable climate, different from anything mammoths had previously experienced. The vegetation that returned wasn't identical to earlier tundra, but was often impoverished, with lower productivity and different species composition. More critically, the cold period was relatively short in geological terms, just over 1,000 years, which wasn't long enough for mammoths to fully recover population numbers or genetic diversity. When conditions warmed again at the end of the Younger Dryas, forests returned even more aggressively, and mammoth habitat contracted faster than before. By this time, human populations were rebounding and spreading, and hunting pressure increased. The combination proved fatal. By around 4,000 years ago, the last woolly mammoths died out on Wrangel Island in the Arctic Ocean, ending a lineage that had existed for millions of years. Mastodons in North America faced a similar but distinct crisis. These elephant relatives were browsers rather than grazers, feeding on leaves, twigs, and shrubs rather than grass. During warm periods, they thrived in the forests and woodland edges of North America. The Younger Dryas transformation of these forests into tundra eliminated their food sources. Mastodon remains from late in the Younger Dryas show signs of nutritional stress, smaller body sizes, thinner bones, and evidence of starvation. Unlike mammoths, mastodons couldn't adapt to grassland environments. Their tooth structure, digestive system, and feeding behavior were specialized for browsing. When forests disappeared, mastodons had nowhere to go. Populations crashed, and although some individuals survived into the early Holocene, when forests returned, the species never recovered. The last mastodons likely died out around 10,000 years ago, victims of habitat loss and human hunting. Giant ground sloths, massive, slow-moving herbivores that could reach the size of modern elephants, inhabited North and South America. Species like Megatherium could rear up on their hind legs to reach tree branches, using their powerful claws to pull down foliage. These animals were adapted to a variety of habitats, from grasslands to forests. But they shared a critical vulnerability: slow reproductive rates. Large-bodied animals typically reproduce slowly, producing few offspring over long generation times. This strategy works in stable environments, but becomes a fatal liability when conditions change rapidly. The Younger Dryas disrupted the vegetation communities that sloths depended on, reducing food quality and availability. At the same time, human populations were expanding through the Americas, armed with Clovis points and other effective hunting weapons. Ground sloths, slow-moving and lacking defensive weapons beyond their claws, were vulnerable to coordinated human hunting. The combination of climate stress and hunting pressure pushed them toward extinction. By the end of the Younger Dryas, or shortly after, most giant ground sloth species had vanished. The debate over whether climate change or human hunting was the primary driver of Pleistocene megafaunal extinctions has raged for decades, with the truth likely involving both factors working in concert. The Younger Dryas provides evidence for the overkill hypothesis because extinctions accelerated dramatically during and immediately after this period, coinciding with both climate chaos and the spread of sophisticated human hunting cultures. Sites showing mammoth kills with Clovis points in direct association prove that humans were hunting megafauna. The rapid human population expansion through previously unpopulated regions would have subjected naive prey species to suddenly intense hunting pressure they had never experienced. At the same time, the climate crisis reduced populations, fragmented habitats, and stressed animal health, making populations more vulnerable to any additional pressure. Together, these factors created a perfect storm of extinction. Some species survived by adapting to ecological niches that remained stable, or by existing in regions where both climate impacts and human hunting pressure were less intense. Bison adapted from being forest browsers to grassland grazers, allowing them to thrive as grasslands persisted in central North America. Musk oxen survived in Arctic regions where human populations remained low and tundra persisted. White-tailed deer adapted to edge habitats and could thrive in both forests and clearings, allowing them to survive the changing landscapes. But the true giants, mammoths, mastodons, giant sloths, saber-toothed cats, and many others, couldn't adapt fast enough. By the time the Younger Dryas ended and the Holocene warming began in earnest, the age of megafauna was over. The landscapes they had shaped for hundreds of thousands of years would never see their like again, and human beings would emerge as the dominant large animals across most of the planet. The North American catastrophe. North America experienced the Younger Dryas as a multi-layered catastrophe that reshaped both its ecology and its human cultures. The continent had been home to a spectacular array of Ice Age megafauna and supported increasingly sophisticated human populations who had mastered Ice Age survival strategies. The Clovis culture, named after a site in New Mexico where distinctive projectile points were first identified, represents one of the earliest widespread cultures in North America. These people had developed extremely effective hunting technologies and had spread across the continent from Alaska to Mexico in a remarkably short time. Then the Younger Dryas arrived and everything changed. The climate whiplash hit North America with particular severity. The megafauna that Clovis peoples had specialized in hunting began disappearing, and human populations were forced to adapt or perish. The environmental transformation was dramatic. Much of Canada, which had been emerging from beneath the Laurentide ice sheet, saw that retreat halt and reverse. The ice sheet stabilized and even advanced in some sectors, reclaiming land that had just become ice-free. The forests and grasslands that had begun colonizing newly exposed terrain were destroyed. South of the ice margin, the climate became bitterly cold and dry. The Great Plains, which had supported herds of horses, camels, and mammoths during the preceding warm period, became a harsher environment. Lake levels fluctuated wildly as precipitation patterns shifted. Some regions became more arid, while others experienced increased moisture. The instability made it difficult for both animals and humans to predict where resources would be available from year to year. Clovis culture effectively ended during or shortly after the onset of the Younger Dryas, though debate continues about whether the climate event caused this or merely coincided with cultural changes already underway. What's certain is that the distinctive Clovis points, large, fluted spear points requiring significant skill to manufacture, stop appearing in the archaeological record right around the boundary. They're replaced by a variety of regional point styles that collectively represent the Folsom and later Paleo-Indian cultures. This diversification suggests that the cultural unity represented by Clovis gave way to regional adaptations, as populations dealt with changing conditions and resources in different ways. Some regions show continuity in settlement patterns and technology, while others show dramatic breaks, possibly reflecting population replacement or migration. The disappearance of megafauna accelerated during this period in what's known as the Pleistocene overkill. Whether this was primarily due to climate change, human hunting, or some combination remains hotly debated. Evidence exists for all scenarios. Kill sites prove humans were hunting mammoths, mastodons, and other large game. Climate data show these species' habitats were shrinking and changing rapidly. Population genetics from preserved mammoth remains show declining genetic diversity consistent with populations under severe stress. What seems clear is that populations already stressed by climate disruption would have been more vulnerable to hunting pressure. A healthy, widespread population can sustain some level of hunting. A fragmented, stressed population pushed into marginal habitats by climate change cannot. The Younger Dryas may have been the climate shock that tipped the balance toward extinction for species that might otherwise have survived into the modern era. Human populations responded to these changes in various ways. Some groups became more mobile, abandoning permanent or semi-permanent camps in favour of seasonal rounds that tracked remaining resources. Others intensified their use of plant foods and smaller game, reducing dependence on megafauna. The archaeological record shows increased use of grinding stones and plant processing tools during and after the Younger Dryas, suggesting a broad-spectrum revolution where diets diversified beyond large game. This adaptation would prove crucial because it made human populations less dependent on any single resource. Those groups that successfully broadened their subsistence base were better positioned to survive the continued extinctions and environmental changes. Regional variations in Younger Dryas impacts created different adaptive pressures. In the Pacific Northwest, marine resources and salmon runs provided buffers against inland climate chaos. Coastal populations could access fish, shellfish, and sea mammals that were less affected by terrestrial climate fluctuations. These groups maintained relatively stable populations and cultural continuity. In the Great Basin, populations adapted to desert conditions that intensified during the Younger Dryas, developing sophisticated knowledge of desert plants and seasonal water sources. In the eastern woodlands, the transition from Clovis to later cultures involved shifting from big game hunting to more generalised foraging in increasingly forested landscapes as the Younger Dryas ended and forests returned. Each region's story is unique, but all involve rapid adaptation to changing conditions. The genetic legacy of the Younger Dryas is written in the DNA of modern Native American populations. Studies show evidence of population bottlenecks and founder effects that correspond to this period, suggesting population sizes crashed before recovering. Some genetic lineages disappear from the record during this time window, indicating that some populations went extinct entirely. The genetic diversity of modern Native American populations is lower than would be expected if populations had grown steadily without major disruptions, consistent with severe population reductions followed by expansion from survivor populations. These genetic patterns tell a story of crisis, survival, and recovery that complements what archaeology reveals about changing material cultures and settlement patterns. The North American continent that emerged from the Younger Dryas was fundamentally different from what preceded it. The megafauna were gone or going. The ice sheets were in their final retreat, exposing new lands, but also changing drainage patterns, sea levels, and regional climates. Human populations, reduced but resilient, had adapted new technologies and strategies. The stage was set for the Holocene, the current warm period, and the eventual development of complex societies, agriculture, and the diverse Native American cultures that Europeans would encounter thousands of years later. But none of that would have been possible without the survivors of the Younger Dryas, those who endured 1,000 years of climate hell and lived to rebuild their world. Seeds of agriculture. The Younger Dryas created a crisis in the Near East that may have forced one of the most important innovations in human history: agriculture. Before this cold snap, Natufian peoples in the Levant had developed an increasingly sedentary lifestyle based on intensive harvesting of wild cereals, wheat, barley, and rye, that grew in dense stands across the landscape. The Natufians had built permanent villages, developed sophisticated grinding stones for processing grain, and created storage facilities for keeping harvested seeds throughout the year. They were so successful at wild plant exploitation that they could support larger, more stable populations than typical hunter-gatherers. They were, in essence, pre-agricultural people who had all the technology and social organization needed for farming, but hadn't yet taken the final step of deliberately planting crops. Then the climate changed, and that comfortable existence became impossible. The Younger Dryas transformed the Levantine landscape from Mediterranean woodland with abundant wild grains to cold, dry steppe, where those plants became scarce and unpredictable. The wild wheat and barley that had carpeted hillsides shrank to scattered patches in favoured locations. The reliable seasonal patterns that Natufian peoples had depended on became erratic. Some years the rains came, the plants grew abundantly, and harvests were good. Other years the rains failed, the grasses withered, and starvation loomed. The settled villages that had been viable during good times became death traps during bad years. Too many mouths to feed from shrinking wild resources. Archaeological evidence shows that many Natufian villages were abandoned during the Younger Dryas, and those that remained occupied became smaller and less permanent. But some groups responded to this crisis by taking control of their food supply. Instead of relying on finding wild grain stands, they began deliberately saving seeds and planting them in cleared plots where they could be tended and protected. This shift from gathering to cultivating wasn't revolutionary at first. It likely seemed like a simple extension of existing practices. Natufian peoples already had extensive knowledge of plant life cycles, seed germination requirements, and optimal growing conditions from their harvesting activities. They knew which plants were most productive, which seeds stored well, and which areas had the best soil and water. Applying that knowledge to deliberate cultivation was a logical step when wild stands became unreliable. But the consequences of that step would transform human civilization. The earliest evidence for cultivation appears in sites like Abu Huraira in Syria, where plant remains show morphological changes consistent with human selection. Wild cereals have seed heads that shatter easily, dispersing seeds when they ripen, a successful strategy for wild reproduction, but problematic for harvesting. As people began collecting and replanting seeds, they unconsciously selected for mutant plants whose seed heads didn't shatter, making them easier to harvest, but dependent on human intervention for reproduction. This represents the beginning of domestication, the evolutionary process by which wild plants become crop plants through human selection. The transition happened during the Younger Dryas and accelerated in its aftermath, suggesting that the climate crisis provided the pressure that made agriculture necessary. The development wasn't limited to cereals. Evidence from this period also shows intensive use of legumes like lentils and chickpeas, which were also being selected and eventually domesticated. These plants provided crucial protein and nutrients that cereals alone couldn't supply, creating a balanced agricultural package that could support human populations without animal protein from hunting. Figs may have been one of the earliest domesticates, with cultivated fig remains from Jordan predating cereal domestication slightly. The pattern shows people intensifying their use and management of multiple plant species simultaneously, creating the foundation for agricultural economies. This transition wasn't simple or inevitable. Agriculture requires more labour than hunting and gathering. Fields must be cleared, planted, tended, and harvested. Early crops were less productive than modern varieties, meaning people had to work harder for each calorie. Reliance on a few crops, rather than diverse wild foods, made populations vulnerable to crop failures. Early agriculturalists were less healthy than their hunter-gatherer ancestors, suffering from more nutritional deficiencies, dental problems, and infectious diseases that spread in settled communities. So why did people adopt agriculture? The answer lies in population pressure and reduced alternatives. Once populations had grown during the good times before the Younger Dryas, they couldn't easily shrink back when conditions worsened. Agriculture, despite its costs, allowed more people to survive on the same landscape than hunting and gathering could support under deteriorated conditions. The social consequences of agriculture began immediately. Permanent villages became established features of the landscape, growing larger as agricultural surpluses supported more people. Social hierarchies developed as some individuals controlled better lands or accumulated larger stores of grain. Warfare increased as groups competed for productive territories and defended their crops and stores from raiders. Religious complexity grew, with elaborate burial practices and eventually monumental architecture appearing in early agricultural societies. The Younger Dryas crisis didn't just force agricultural adoption, it triggered a cascade of social transformations that would lead to civilization as we know it. Cities, writing, metallurgy, empires, all of these eventually emerged from the agricultural foundations laid during and after the climate catastrophe. Regional variations in agricultural development show how different environments and cultures responded to similar pressures. In China, rice cultivation developed independently along a similar timeline, likely also driven by climate stress and population pressure. In Mesoamerica, maize domestication followed several thousand years later, showing that agricultural transitions occurred repeatedly when conditions were right. But the Near Eastern development remains the earliest and best documented, and it's intimately tied to the Younger Dryas crisis. Without the climate shock that made wild food gathering unreliable, agriculture might have developed much later or not at all. The 10,000-year winter didn't just test human survival, it forced innovations that would allow human populations to grow from millions to billions and reshape the entire planet. The irony is profound. The climate catastrophe that nearly destroyed humanity also forced the changes that made modern civilization possible. Ocean currents stopped flowing. The shutdown of Atlantic Ocean circulation during the Younger Dryas represents one of the most dramatic climate system failures documented in Earth's history. The Atlantic meridional overturning circulation is not just a current, but an entire system of interconnected water masses, moving heat, salt, and nutrients throughout the Atlantic basin and beyond. When functioning normally, it transports roughly 1 petawatt of heat energy northward, equivalent to the output of millions of power plants. This heat delivery keeps northwestern Europe remarkably mild for its latitude. London is at the same latitude as frigid Labrador, yet has a far milder climate. The difference is ocean heat transport. When the Younger Dryas shut down this system, the climate impacts were felt across continents and demonstrated how interconnected Earth's climate systems truly are. The mechanics of the overturning circulation depend on density differences in seawater. Warm, salty water from the tropics flows northward as part of the Gulf Stream system. As this water reaches high latitudes around Greenland and the Norwegian Sea, it cools and evaporates, becoming denser. The cold, salty water becomes heavy enough to sink to the deep ocean, forming what's called North Atlantic deep water. This sinking pulls more surface water northward, maintaining the circulation. The deep water then flows southward at depth, eventually upwelling in other ocean basins and returning surface flow to the Atlantic. This conveyor belt moves constantly, redistributing heat and maintaining relatively stable climate conditions in the regions it affects. The freshwater pulse from Lake Agassiz disrupted this delicate density balance. When massive amounts of fresh water, less dense than salt water, spread across the North Atlantic surface, the water became too light to sink no matter how cold it got. The sinking stopped, which meant the pulling force that drew warm water northward disappeared. The Gulf Stream continued to flow because it's also driven by winds and Earth's rotation. But the warm water that would normally have reached high latitudes and released its heat to the atmosphere instead turned southward earlier, mixing with cooler waters before reaching the critical sinking regions. The heat that would have warmed Europe and the North Atlantic stayed farther south, and the climate around the affected region plunged into cold conditions. Evidence for this shutdown comes from multiple ocean-based proxies. Sediment cores from the deep Atlantic show changes in the types of foraminifera, microscopic shelled organisms whose species composition reflects water temperature and chemistry. During the Younger Dryas, warm water species disappear from North Atlantic sediments and are replaced by cold water species, indicating a dramatic temperature drop. But more tellingly, the patterns of forum species distribution show that North Atlantic deep water formation, visible in the sediment record through specific species assemblages, ceased during the Younger Dryas. The deep water flow that should have been forming in the Norwegian and Greenland seas stopped, replaced by different water masses flowing from other sources. The conveyor belt had indeed shut down. Chemical traces in the sediments confirmed this interpretation. The ratio of different carbon isotopes in forum shells reflects the sources of the water masses they lived in. North Atlantic deep water has a distinctive isotopic signature derived from its formation processes. During the Younger Dryas, this signature disappears from the deep Atlantic sediment record, replaced by signatures indicating water masses from southern origins. This means the deep water filling the Atlantic basin was coming from different sources, not from the North Atlantic sinking regions. The circulation had reorganized into an entirely different pattern, one that didn't deliver heat to the north. Ice cores from Greenland record the atmospheric consequences with painful clarity. The oxygen isotope ratios in the ice, which reflect temperature, show a sharp drop at the onset of the Younger Dryas, with temperatures plummeting roughly 15 degrees Celsius in some reconstructions. This cooling happened over a span measured in decades at most, possibly just years. The ice cores also show changes in the types of dust and sea salt deposited, indicating that wind patterns shifted dramatically. Storm tracks moved, precipitation patterns changed, and the entire atmospheric circulation over the North Atlantic reorganized in response to the suddenly altered ocean heat distribution. The system had flipped to a new state, and it would remain locked there for over a millennium. The stability of the shutdown state demonstrates another crucial aspect of climate systems. They can have multiple stable configurations. Earth's climate during the Younger Dryas was stable in the sense that it didn't randomly fluctuate, but maintained a consistent cold state year after year, century after century. This wasn't because conditions couldn't change, but because feedback mechanisms reinforced the shutdown. The fresh water that initiated the event dispersed over time, but by then other factors had kicked in. Increased sea ice coverage prevented water from cooling and sinking effectively. Atmospheric circulation patterns adjusted to the new ocean state and helped maintain it. Multiple reinforcing feedbacks locked the system in the cold configuration, and it required a substantial push to break it out. The termination of the Younger Dryas shows this clearly. Ice cores reveal that the end came as abruptly as the beginning. Temperatures shot upward in a matter of decades, returning to warm conditions. This suggests that the system finally crossed a threshold where the feedbacks maintaining the cold state were overcome, allowing circulation to restart. Once the conveyor belt began flowing again, positive feedback helped it strengthen rapidly. Warm water flowing north released heat that melted sea ice, which allowed more water to sink, which pulled more warm water north. The system flipped back to its warm state as quickly as it had shut down. This behavior, long periods of stability punctuated by rapid transitions, is characteristic of complex systems with multiple stable states, and it has profound implications for understanding modern climate risks. If current climate change were to trigger a similar shutdown through Greenland ice melt, the rapidity and magnitude of the response might be far greater than gradual warming projections suggest. Ancient humans adapt or die. The human population scattered across the Northern Hemisphere during the Younger Dryas faced a stark choice: adapt to the radically changed conditions or perish. This wasn't a slow climate drift allowing gradual cultural evolution. It was a shock that required immediate responses. Food sources disappeared, water sources froze, materials for tools and clothing became scarce, and territories that had supported communities for generations became uninhabitable. The archaeological record shows both the catastrophic impacts and the remarkable resilience and innovation of the people who survived. Those who made it through developed new technologies, new social strategies, and new ways of understanding their world that would shape human development for millennia to come. The most immediate challenge was securing adequate nutrition in environments where food had become scarce and unpredictable. Before the Younger Dryas, successful hunter-gatherers maintained detailed knowledge of seasonal patterns, when specific plants fruited, when fish spawned, when game migrated. This knowledge was accumulated over generations and passed down through oral traditions. But the climate chaos disrupted these patterns. Plants that had reliably appeared in certain seasons failed to grow. Fish runs became erratic or ceased. Game animals changed their migration routes or disappeared entirely. The knowledge systems that had sustained peoples for thousands of years suddenly became unreliable guides. Survival required abandoning old certainties and developing new strategies through experimentation and observation. Some groups responded by increasing mobility. Instead of maintaining semi-permanent base camps and making seasonal rounds to specific resource locations, they became more opportunistic and wide-ranging. Archaeological sites from the Younger Dryas period often show shorter occupation spans and less investment in structures compared to earlier and later periods. People were moving more frequently, not establishing deep roots in any one location. This strategy reduced vulnerability to local resource failures. If food became scarce in one area, the group could move to another. But it also had costs. Highly mobile groups can't accumulate many possessions. They can't invest in permanent infrastructure. Children and elderly must travel constantly, limiting population growth and survival rates. Other groups intensified their use of previously marginal resources. Evidence shows increased exploitation of fish, shellfish, birds, and small mammals during the Younger Dryas. Sites show more fish bones, more bird bones, and tools associated with fishing and fouling become more common. This broad-spectrum revolution meant working harder for each calorie. Catching fish or snaring birds requires more effort per unit of meat than killing a mammoth or bison, but it provided a buffer against the collapse of megafauna populations. Groups that successfully diversified their diets were more resilient to fluctuations in any single resource. This adaptation would prove crucial not just for surviving the Younger Dryas, but for long-term human evolution. Modern hunter-gatherer groups typically have highly diverse diets, and this pattern likely intensified during climate crises like the Younger Dryas. Technological innovation accelerated under pressure. The development of microliths, tiny stone blades that could be hafted into wooden or bone handles to create composite tools, appears in many regions during or shortly after the Younger Dryas. These tools were more efficient than earlier designs, getting more cutting edge from each piece of stone and allowing easier repair and maintenance. Bone and antler working became more sophisticated, with elaborate barbed points and harpoons appearing in the archaeological record. Sewing needles with eyes became finer and more common, reflecting the importance of well-made, warm clothing in the harsh conditions. Each innovation represented someone experimenting, succeeding, and passing that knowledge on, a process accelerated by the desperate need for better solutions. Social adaptations were equally important. Evidence suggests that group sizes may have shifted during the Younger Dryas. Some researchers argue that groups became smaller and more flexible, allowing them to exploit scattered resources more effectively. Others point to evidence of larger aggregations at certain resource-rich locations, suggesting people gathered seasonally at places where food remained available. Both patterns likely existed in different regions and contexts. What's clear is that social flexibility, the ability to fission into smaller groups or aggregate into larger ones as conditions demanded, was crucial for survival. Groups that maintained rigid social structures probably suffered higher mortality than those that could adapt their organisation to circumstances. Violence likely increased as stressed populations competed over shrinking resources. While clear evidence is limited, some sites show increased rates of traumatic injuries consistent with interpersonal violence. Defensive positions of settlement suggest increased concern about raids or attacks. Competition between groups for productive territories would have intensified as those territories shrank and became more valuable. At the same time, exchange networks and alliances may have become more important for survival. Groups that maintain trade relationships could access resources from multiple regions, buffering against local failures. The balance between competition and cooperation would have varied by region and circumstance, but both strategies shaped how populations navigated the crisis. Spiritual and cosmological systems likely underwent profound transformations. For peoples whose understanding of the world was built on predictable natural cycles, the Younger Dryas would have represented a cosmic catastrophe. The sun still rose and set, seasons technically still changed, but the world no longer behaved as it should. The game didn't appear when expected. Plants didn't grow in their season. Winters became unbearably long and cold. How did people make sense of this? We can't know their thoughts, but changes in burial practices and symbolic artifacts during this period suggest spiritual turmoil. Some groups created more elaborate burials, possibly reflecting increased concern with death and the afterlife. Others abandoned previous ritual sites and created new ones. The very concept of how the world works and humanity's place in it was probably being renegotiated. The population bottleneck created by the Younger Dryas had lasting genetic consequences. Populations that maintained larger sizes and avoided isolation preserved more genetic diversity. Those reduced to small, fragmented groups lost diversity through drift and inbreeding. Modern genetic studies show signatures of these ancient bottlenecks: reduced diversity in certain lineages, expansion signatures from survivor populations that grew and spread after conditions improved. The people who emerged from the Younger Dryas were not just culturally changed, but genetically different from those who entered it. The crisis acted as a filter, selecting for populations and individuals with the adaptability, resilience, and innovation to survive conditions that killed others. Modern humans are, in very real ways, descendants of Younger Dryas survivors, inheritors of the traits and traditions that allowed our ancestors to endure when easier paths would have led to extinction. Ice cores tell the story. The detailed reconstruction of the Younger Dryas would be impossible without ice cores, cylindrical samples drilled from the great ice sheets of Greenland and Antarctica. These cores are time machines, preserving annual layers of snow that fell and compressed into ice over thousands of years. Each layer contains information about the climate conditions when it formed: temperature, atmospheric composition, precipitation levels, volcanic activity, and more. Reading ice cores requires sophisticated analytical techniques and careful interpretation, but the resulting records provide unmatched detail about past climate. The cores from Greenland, in particular, have revolutionized understanding of the Younger Dryas, revealing not just that it happened, but precisely when, how quickly, and how severe the climate changes were. Ice cores are drilled using specialized equipment that extracts cylindrical samples from the ice sheet without disturbing the layers. The deepest cores reach back hundreds of thousands of years, with each meter of depth representing roughly 1 decade of time in the upper sections and longer periods deeper down, where ice has been compressed. The cores are immediately frozen and transported to laboratories where they're analyzed using multiple techniques. Each analytical method extracts different information from the ice, and when combined, they provide a comprehensive picture of past climate and environment. The process is meticulous. Contamination must be avoided, measurements must be precise, and interpretation must account for complex processes that affect how signals are preserved in ice. The primary climate proxy in ice cores comes from oxygen isotope ratios. Water molecules contain oxygen atoms, which exist in two stable forms, lighter oxygen 16 and heavier oxygen 18. The ratio between these isotopes in ice reflects the temperature when the snow fell. Colder temperatures favour incorporation of lighter isotopes, so ice formed during cold periods has different isotope ratios than ice from warm periods. By measuring these ratios down the length of an ice core, scientists construct a temperature history. The precision is remarkable. Changes of even 1 degree Celsius can be detected. For the Younger Dryas, the isotope record from Greenland shows a sharp excursion toward cold values lasting roughly 1,300 years, bounded by abrupt transitions that took decades or less. Air bubbles trapped in ice provide actual samples of the ancient atmosphere. As snow compresses into ice, small pockets of air become sealed in bubbles. These bubbles contain the atmospheric gases present when the bubbles were sealed, creating direct samples of ancient air. By analysing the composition of these bubbles, scientists can measure past atmospheric carbon dioxide, methane, and other greenhouse gas concentrations. The Younger Dryas show interesting patterns in these gases. Carbon dioxide levels were generally rising as the world warmed out of the Ice Age, but the rise paused during the Younger Dryas before resuming afterward. Methane levels, which respond quickly to changes in wetland area and tropical rainfall, show a dramatic drop during the Younger Dryas, indicating widespread drying and cooling in the tropics. Annual layers in ice cores can be counted like tree rings, providing direct dating of climate events. In the upper sections of Greenland ice cores, annual layers are visible to the eye. Summer snow looks different from winter snow due to differences in grain size, dust content, and sometimes density. These layers can be counted down the core, providing dates without need for other dating methods. For the Younger Dryas, this annual layer counting has been done multiple times by different research groups, all arriving at consistent results. The event began approximately 12,850 years ago and ended approximately 11,650 years ago, lasting roughly 1,200 years. The precision of this dating allows correlation with other climate records worldwide, showing whether changes in different regions happen simultaneously or in sequence. Chemical analysis of ice reveals other environmental changes. The concentration of sea salt aerosols indicates wind strength and sea ice extent. During the Younger Dryas, sea salt concentrations in Greenland ice increased dramatically, suggesting windier conditions and more sea ice producing salt spray. Dust concentrations also increased, indicating either more exposed land surface, less vegetation, or stronger winds carrying dust from distant sources. The chemistry of the dust can even indicate its source region. During the Younger Dryas, more dust came from Asian sources, suggesting changes in atmospheric circulation patterns. These chemical signals paint a picture not just of cold temperatures, but of a landscape stripped of vegetation, whipped by fierce winds, and surrounded by extensive sea ice. Volcanic ash layers in ice cores provide important dating markers. Major volcanic eruptions inject ash into the stratosphere, where it spreads globally before settling out over months to years. When this ash falls on ice sheets, it creates a distinctive layer that can be identified by its chemical composition. If the same volcanic layer appears in ice cores from multiple locations, it provides a tie point for synchronizing the cores. Several volcanic layers have been identified in ice spanning the Younger Dryas period, allowing precise correlation between Greenland and Antarctic ice cores. Interestingly, these correlations show that the Antarctic didn't experience cooling during the Younger Dryas. In fact, it may have warmed slightly. This pattern supports the ocean circulation hypothesis. When heat stopped being transported to the Northern Hemisphere, it accumulated in the Southern Hemisphere instead, creating what's called a bipolar seesaw pattern. The abruptness of transitions recorded in ice cores is one of their most striking features. When scientists zoom in on the boundaries at the start and end of the Younger Dryas, they find temperature changes happening over spans of just a few decades. In some high-resolution cores, the transitions appear to take less than 10 years, almost instantaneous in geological terms. This rapidity has profound implications. It means climate doesn't just drift slowly between states, but can flip rapidly when thresholds are crossed. It means human societies experiencing such transitions wouldn't have generations to adapt, but would face catastrophic change within a single human lifetime. And it means the climate system contains the potential for abrupt changes that wouldn't be predicted by simple models, assuming smooth, gradual transitions. Modern ice core drilling continues to refine understanding of the Younger Dryas and other climate events. Newer cores use improved drilling technology to preserve ice with less disturbance. Analytical techniques constantly improve, extracting more information from each sample. International collaboration allows cores from different sites to be compared and synthesized. The result is an ever more detailed picture of past climate variability, and that picture contains warnings. The climate system has repeatedly demonstrated its capacity for rapid severe changes when pushed past certain thresholds. The Younger Dryas serves as a stark example of what Earth's climate can do, recorded in exquisite detail in layers of ancient ice that refuse to let us forget. Those frozen archives tell a story of a planet pushed to the brink, and the humans who survived against all odds.